It's okay, just in case you guys want to play around with the... You don't have to. Right?
Are we allowed to use the regular calculator on the test? Or you put it up there on the board?
No, you don't really need it.
There it is. There we go.
What is it?
Oh, it's still there.
Wait, no. That one's for sale.
What are you guys talking about?
She found one in here.
I found a graphing calculator and like it left a note for someone to call me.
Where's it for sale sign?
And nobody called you?
Statute of limitations, I believe it's yours now. You know, by the whole, law of finders keepers.
89.
No, I don't want to keep it. I already have a graphing calculator. It's like way nicer.
Alright, so today we're doing parametric curves. We'll do some, today's going to be a pretty, a light-hearted day, with bunnies and happy thoughts, rainbows, so we'll do that, and then on Tuesday when we get back, we can review for the exam all sometime soon, probably this weekend when I get caught up. I'll email you guys out some stuff. But if you guys want to start studying, you guys should do the chapter review problems for chapter 10. So that's what the exams are. Okay, so let's just talk a little bit about parametric curves. So you know how normally we graph when we plot curves either as we have y is equal. Actually, let me use a different, because I'm going to use f for the parametric curve. Let's just make up a letter, maybe h of x. So you write y as a function of x, or you write x as a function of y. Let's see, how about r of y? Right? So, for example, if you graph y equals to x squared, well, that's a parabola, right? And if you graph x, I don't like that there. Okay, if you graph x equals to y squared, what does that look like? Parabola.
Sideways.
Yeah, facing to the
Right.
to the right. Okay. But there are a lot of curves that we can't actually graph this way. Can you guys think of one? The simplest example of a graph? Yeah, a circle, right? So the circle we can't write as a function because it's not a function, right? So to plot a circle, right? So like you have x squared plus y squared equals to 1. This is the equation of a circle, but you can't write it as a function. You can solve for y, and when you solve for y, you get plus or minus the square root of 1 minus x squared. So you can plot the circle, but you have to plot it as two separate pieces. Okay, so that's just one example, but there are other curves that we want to look at that just simply cannot be described this way. So you come up with an alternative. You say, okay, what if you say that you are going to describe a curve in terms of another variable and we're going to use t, and t is the most common letter because you can think of it as time. So, but it doesn't have to be t, where both x and y are functions of t. So you have, let's me see, how about blue? Okay, so x is a function of t, and y is equal to, let's say, g of t. So you have two functions, and each one of them describes the x and the y values, but both of them are in terms of t. Okay, so it's just a different way of writing. So, all right. So then the curve C of t, which has coordinates, let's see, so C of t is equal to f of t for the x values and g of t for the y values, is called a parametric curve. Okay, so basically what you have is these are the x values and these are the y values. And this, so setting curves up this way allows you to draw some very, very, very interesting curves. So let's start off with a simple example. So let's say you want to look at the curve given by, let's see, how about, I had one here, t minus 2 and t squared minus 2t. So this curve, it has x values, the x values are given by t minus 2, and the y values are given by t squared minus 2t. So just to kind of get a feel for this, let's do a little table just to get our feet wet. Now, we aren't going to do this very often, so you might feel like you're going back to grade school. But we'll just do this for a little bit. So why don't you guys pick some values of t for me? Anything. It could be whatever. You know, pick something simple.
1.
Okay. So 1. So when, well, how about we do 0, and then we'll do 1. So when t is equal to 0, x is equal to negative 2, y is equal to 0. Okay. And let's do 1. When t is equal to 1, x is equal to negative 1, y is equal to negative 1. Okay, how about 2? X is 0, y is 0. Let's do 3. When t is equal to 3, x is equal to 1, y is equal to 9 minus 6, which is 3. How about a negative value for t? So when t is equal to negative 1, then it's x is equal to negative 3. And when t is equal to negative 1, y is equal to positive 3. Okay, so let's see if we can just kind of, at least somewhat, see what this looks like. So, let's see. So I have the first point, and actually, well, let's plot these right here. So I have, when t is equal to 0, x is negative 2, 0. So that's right here, right? And then my next point is at negative 1, 1. So that's negative 1, negative 1. So that's down here, right? So that's my second point. So let's do this. Okay. So that's my second point. My third point is at 0, 0, right there. My third point is 1, 3. So I have 1, 3. And then this one actually that we picked, this one was before, right? So this one is at negative, when t is negative 1, x is negative 3, 3. So negative 3, up 3. So what does that kind of look like?
Parabola.
Yeah, it kind of looks like a parabola, right? Okay, now, so if we connect the dots, we get a parabola. So that wasn't very exciting, right? One thing that is different, though, is that parametric curves have a direction. So if you think of the t values as time, then what's the direction that it's moving? Is it going left to right or right to left?
For us, left to right.
It's going left to right, right? Because this is t equals -1, t equals 0, 1, 2, 3. So it's moving in this direction. So typically you put little arrows in the direction that it's moving. Okay? All right. So, that wasn't very exciting. Like, oh, well, what, we already knew how to write parabolas, right? And actually, if you wanted to, so this is by plotting points, right? And we could also, since notice that you have x equals to t minus 2 and y equals to t squared minus 2t, sometimes what you can do is you can remove the parametrization. So that means rewrite it so that you can put either y in terms of x or x in terms of y. And it makes sense that you should be able to do this, right, with this one, because it actually turns out to be a parabola. So how would we do that? Yeah, solve for t on one and then plug it into the other, right? Only makes sense, right? So from this one, we would get that t is equal to x plus 2, right? And so then we can put that into the t's over here. So what we're doing here in this little box is we're unparametrizing. So we're removing the parametrization. So, okay, so let's do just a little algebra to confirm that that's actually a parabola. Because, we didn't plot all the points. Maybe we missed something. So, hello. Okay. All right, so then I have that y is equal to t squared. So I have x plus 2 squared minus 2 times x plus 2, right? Okay. And then you have y is equal to, if I square this, what would I get?
X squared plus 4x plus 4.
Okay, x squared plus 4x plus 4. And then minus 2x minus 4. So then I get that y is equal to x squared plus 2x. And if you just look at the zeros of this, right, those are at 0 and -2, which are exactly the zeros right here on our graph, right? Okay, so if you have a parametric curve, so right here what we did is we plotted points, right? And this is good if you have a lot of time on your hands, or if you plug it into a calculator. Well, that's what the calculator does, right? It just plots the points and it gives you a picture. What do you guys think about this? It's kind of like it's good to know that it's possible, but if you can write it in terms of one of the variables, well, then what's the point of having parametric curves, right? Is that how you feel? Yeah, right? That's kind of how you should feel. It's like, well, what's the whole point of doing this if it's just the same as it was before, right? Just write it how it was, or just write it as a parabola, right? Okay. So, anyways, okay. Okay. Now, so let's take a look at something else. Maybe something that wouldn't require us to plot any points. Something that we can figure out. So let's say you have the parametric curve defined by, let's say, x is 3 cosine t, and let's say y is, actually, why don't we do this? Let's start off with just cosine t and sine t, and then we'll add stuff as we go. See if we can figure out what changes. All right. So cosine t, so x is cosine t, y is sine of t. What is it?
Oh, it's is it cotangent?
Mm-mm. Nope. Any ideas? The x values are the values of cosine. The y values are the values of sine. It's a circle, right? Because that's how you define sine and cosine on the unit circle as the x value of the point. So to see this, what you can do is you know that, so we know that, well, let me write it like this. Cosine squared plus sine squared is equal to 1, right? We know this. Why? It's an identity, right? So the Pythagorean identity. Okay, but what is cosine? Cosine is equal to x, right? This is the x value and this is the y value, right? So what this tells you is, so cosine squared plus sine squared is equal to 1. So that means that x squared plus y squared is equal to 1, right? So that's the exact equation of the unit circle, right? So that's... Okay, but then remember we said that parametric curves have a direction. So what do you guys think about that? What direction is it going in? So when you're not sure for the circle, it's kind of obvious that it's rotating counterclockwise, right? Because as if you start from at t equals 0, then you start moving in this direction, right? Just because of what you know about sine and cosine. But if you don't know, what you start doing is you just plug in points so that you can kind of see the general direction. But you always think of t as being representing time. So you start, say, you don't have to start at 0, but you can think of it as starting at time equals 0 and seeing over time, if you plug in a few points, what direction is it going in. Does that make sense? Okay, now, so let's say now I add a little something here. Let's say, so I'm going to rewrite it. But I'm going to so this is the same, except that I'm now restricting t to go from 0 to 4 pi. So what does that mean? Yeah, t is going from 0 to 4 pi, right? So from when t goes from 0 to 2 pi, that's 1 revolution, right? When t goes to 4 pi, then it's retracing. So this traces the circle exactly 2 times. Okay, so this is, it's important so the picture looks exactly the same, right? But you're going around twice. So this is important later on for when we're going to be doing, calculus stuff. Okay, now let me change some other things here. How about, let's say I change the argument of sine and cosine. So they're both 2t.
Bigger circle.
Because
it goes around twice as fast.
Twice as fast, right? So this again looks exactly the same, but this changes the period. It cuts the period in half. So now it's going to go around twice as fast, right? Okay, so twice as fast. Twice as fast. But again, it's still going to look exactly the same, right? Twice as fast. Okay, so now this is where it gets interesting. What if I now remove, let's say that one. So I leave the 2t on the sine, but I take it away from cosine. So what does that mean? What's going to happen?
Fast and slow.
Yeah, one is going faster than the other, right? So the x value is moving. So as the x value is changing,
The y value
like this,
changes twice as fast.
exactly. So what do you guys think this is gonna look like?
An ellipse.
If the cosine is moving.
So this is definitely much harder to visualize. Let's all right. Let's call up our little buddy here, Wolfram, so that we can play. Let's play. Dun, 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 dun.
That looks way crazier than I thought it was going to.
Hello.
How are you getting connection on the first round?
I was kind of wondering the same thing myself.
It's tethering on my
Oh.
phone.
Oh.
What?
The home Wi-Fi, yeah.
What do you mean you're not connected? Of course I'm connected. How dare you? How dare you?
Somewhere Steve Ballmer's laughing right now.
What?
Somewhere Steve Ballmer is laughing right now.
Wait. Where is it? Oh, okay. Wait. I turned it off. Oh, shoot. On. 1, 2, 3, go. 1, 2, 3, go. I'll have to edit this part out.
Can you do it on MATLAB?
Yeah, actually, it's really easy to do it in MATLAB. Actually, I can maybe show you, and I'll open up MATLAB. Okay, so let's do.
That's pretty good. I remember that.
Actually, well, why don't we do? Okay, if you don't put parametric plot, if you just do cosine of t, sine of t. Just for the first one, it'll give you all of them. So if you just put it in, put them both in parentheses, it'll give you the graph of both, sine, cosine, and then it gives it to you in a little bit bigger, and then it gives you the parametric plot. But then if you say you only want the parametric plot, well then it'll just give you the parametric plot. So let's make that 2t. And
It's like there's two separate cosine and sine waves, and then sine just has a faster frequency. It's going to be like,
yeah, so it
it'll be twice the frequency of
seriously.
for the same amplitude.
It's like the y value is changing much faster. So it there it is. So it starts going up, but then by the time the x value is halfway, the y value is already back down. So it comes down all the way back down, and then so see how the y value is just moving much faster than the x value can keep up with. So so now we get to play. So let's do 4. What do you guys think that's going to look like?
Oh.
So even faster, right? So you get all kinds of crazy things.
So it's just gonna add if you keep on adding higher. Like if you add 8, it'll just add.
Yeah, see how the x values are moving pretty slow, right? You're moving really slow through the x values, but the y values are like going up and down and up and down and up and down and up and down. That's because the y values are moving much faster than the x values. So the x values are changing really slowly, but it's going up and down and up and down and up and down. So now if we switch them, let's say I do cosine of 2t and just sine of t, what do you guys think that's going to look like? Yeah, the other way, right? So the x values are going to now move much faster, and the y values are going to move slow. So let's take a look at that for fun. What happened?
That's not the right thing.
Does that make sense?
What did you do? What did you switch?
Doesn't it? Because
I just made, so I made cosine, x cosine of 2t, and y is sine of t. Let's make this one bigger, see what happens. So here we have that, let's see. So cosine of 4t, so that would be going through the x values, right? From starting at 1, and then in 2 pi it would end up at back at 1 again, right? No. The x values. You know what it is. Is we need. This is not quite expected. All right, so what's going on? So if we look at t equals 0, what's the first point? When t is equal to 0, cosine is, or x is equal to 1, and then y is equal to 0. So that's this part right here, right? So then when t is equal to, let's say, pi over 2, then what is cosine? When t is equal to pi over
negative 1.
Well, let's say, okay, let's do when t is equal to pi over 4, cosine is 0, right? And then sine is going to be
1.
Pi over 4. Root 2 over 2, right? So then when t is equal to pi over 2, then you have cosine x is negative 1, and then sine is equal to 1, right?
Yeah.
Okay, so then what about if you keep going? So why don't we, well, since this is only giving us part of the graph, and I don't know how to tell it to not, then now is a perfect time to call up FreeMat. Okay, so, you guys ready?
Let's do this.
Let's do this. All right, so what are we going to do? Where do we want t to go from and to? Negative 2 times pi. And increments of 0.1 to 2 pi. Sound like a plan? Okay. And I want x to equal to cosine of 2 times t. Y is equal to sine of 2 times t. Right? And then all you got to do is plot x and y.
Or was it just t, sine of t?
What?
Yeah, it was. So the one.
Oh, yes, it was. Yes. Y is equal sine of t. Thank you. Okay.
put it in
two
twice.
lines there now for sine.
Oh yeah, but it'll just replace the other one.
Oh.
Yeah. Ta-da! So what's happening?
It just keeps going as a parabola.
So what does it do when it gets to? So
But it's going faster in the x direction than in the y direction.
let's do, okay, let's change t. Let's do t goes from we did negative 2 pi to 2 pi. Okay, let's do 0 to 2 pi. Okay, so x equals cosine, y equals 2 sine, and then we plot. Okay, we plot. So what's going on?
Is it tracing itself? Is that what it's doing? It's going back and forth.
Well,
So instead of having the same image mirrored over each other, it's
so notice that the x values are going from 1 to negative 1 to 1 to negative 1. And then the y values are going from 1 to negative 1 to 1 to negative 1, 1 to negative 1, right? So where does it start? So we know it starts here, right? And then once where does it hit? Right here. What was that? What was this angle?
What?
The one up here? That was pi over
is it 2 or 4?
2, right? Yeah, pi over 2. Yes? So what happens when, let's say, 3 pi over 4. So if you plug in, so here, let's do some dun 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 dun. So when t is 3 pi over 4, then what is cosine?
Negative red 2 over 2.
X is negative root 2 over 2. And then y is equal to
Red 2 over 2.
positive root 2 over 2. So it's going back, right? Does that make sense? And then, so then at what point does it go, let's go, so at what point does it start coming down, this bottom part? So what is it back at the initial point? Pi, right? Because when t is equal to pi, then you have x is 1, and then y is...
X is negative 1 and y is 0, right?
No, because it's cosine of... Wait. It's cosine of 2t, no?
2t, yeah.
Is that what I did?
Yeah.
Cosine of... Yeah, I did oh. Did I do it backwards? No. Cosine of 2t, sine of t. Cosine of t, sine of 2t. Oh yeah, because we talked... Oh yeah, we switched it later. Okay, sorry. Oh. Shoot. But this one we did with... No, we did it right. Okay, okay. We did do it with the other one, right? Okay.
Yeah, and that one was like connected.
So right now I think, well, what's happening is I'm confusing myself and you at the same time. So right now we're looking at this one, right? Right? That's the one that we're plotting. So at pi, cosine is, we have cosine of 2 pi, which is equal to 1, and then sine of pi, which is 0. So that's when you go back. And then after pi, then you start going, where is it? Then at pi, then notice that y starts becoming negative. That's because sine is negative after pi. Does that make sense? And then you go back again, and then back again, and retrace over and
So
over.
essentially, the circle is collapsed on itself to the right hand side, and it's just kind of tracing itself. Is that what it's doing?
I probably wouldn't say collapsing itself.
Because This is weird because it's going to a circle, but in a straight line. I don't know how to explain it.
Like fold it in half.
Yeah, kind of like that. It's just kind of
Which way the arrows
Yeah, I was
go?
about
You
to
can't
ask,
really,
like, how do you draw the arrow?
you can't really do that on that one, huh?
Well, right. So sometimes, yeah. I mean, you can have a parametric curve that's going in both, depending on. So it's basically just bouncing back and forth between the two, and yeah. So in this case, you just plot both. It's just kind of going up and down and up and down.
How come it doesn't look like the first one?
Yeah.
Well, because it's not the first one. Because the first one
Don't they have,
is
like, mirror values and stuff?
no. So here, let's do the first one again. So we have the first one was, what was it? Cosine of
T sine 2t.
So that was the first one, right?
Oh, that's-
So here you have, we were at 0, right? And then notice that when t is pi over 4, the y value is 1, and the x value is root 2 over 2, right? So then we're up here. And then after that, then the y value starts decreasing.
So if you
But then you keep going. It's just, yeah, it's different.
if you switch like sine was x and cosine was y, then it would be sideways.
Sine with x. Oh, you mean, so instead of doing x equals to cosine, do x equals to sine, and y equals to cosine.
And one of them cosine is too cheap.
Well, first off, why don't we do this? What do you guys think that's going to look like?
So
Right. Or an oval. Is that just
Yeah, it looks oval, but it's not. It's a circle. Okay, so if we change that, let's see. How about 2 sine t? Oh, sorry. 2 times. So see, you guys can play around with this all day. It's great times. Fun times. There you go. So you can come up with okay. So why don't you guys give me something crazy, whatever. 1, 2, 3, go.
cotangent?
secant.
Do something in
Cotangent of x over 2.
Well, it has to be
Two would be x.
t
Something crazy ridiculous.
squared over 2
Pi
times
e
e to the t to the third. Oh. Okay. All right, let's go with that. All right, what about y? All right, how about
Cosecant.
4 times cosecant of x to the 5th minus log of x.
Oh, you're solving variables there.
gonna look like a
It's just a lot.
No, you solved variables there. You've got t's and x's.
Oh, I did x. Shoot. Oh, I ruined it. All right, let's try again. Oh. So as you can see, doing this by hand is not exactly, the best plan. So obviously we did not pick a good one. Because, well, the numbers are massive, right? This is like times 10 to the 103. And so, yeah, so
What is this? Like a
we
dot?
didn't do a good job.
Let's just do cotan of t and cosecant.
Let's change these to
Cosine 2.
we'll change these to cosine, and then we'll change this one to sine better.
First cosine to 2x and cosecant.
Let's get rid of this e stuff. No. Okay. All right. There we go. Now we've got something.
Wow.
Success. We did it. Maybe we need more definition. There we go.
It'll fill in.
I don't know. I don't know what we did.
What's the scale?
We just-
Like, what's that going
That's
to?
only to 1 because I changed it to sines and cosines. But no. Anyways, those are the kinds of fun times you can have with parametric curves. Okay, so I was not planning on spending that much time doing that, but I did promise fun, so I felt like I had to do some fun. Okay, so let's do. All right, let's talk about the derivative. Derivative and the slope of the tangent line. Okay, so let's say you have a parametric curve, and you have, I don't know, something like that, like how a paper airplane flies or something. And you want to find the slope of the tangent line at a point, right? So here, these are x and y values, right? So the slope of the tangent line is given by the derivative of y with respect to x, right? Do you guys agree with that statement? So slope of the tangent line is equal to derivative of y with respect to x at whatever point you want to find it, right? Yes, yes? Okay. So the problem is, though, that your parametric curve, c of t, so that's a function of t, right? So the x value is given in terms of t, and then the y value is given in terms of t, and you're trying to find the derivative of y with respect to x, right? So this is a problem. So who do you call? Well, you call the... No, you call the... You could call the Ghostbusters, although maybe they could help you. I don't know. They are scientists, so maybe they can. They are smart guys. I remember I watched the movie. If they can destroy a giant marshmallow man, they can probably find the slope of the tangent line. So you call up our old buddy, our old pal, the chain rule. Yay. All right. So then you say, hey, well, I know that. So let's say you have, you find g prime of t. So what's g prime of t? So that's the derivative of. So here, what we have. Let's just make clear that we're using the same notation as last time. So we have x is equal to f of t, and then y is equal to g of t. Okay, so g prime of t is equal to what? dy. Oh,
dt.
dy over dt, right? Okay, but then so if I want to use the chain rule here, then what would this look like? If I want to write dy over dt as dy over dx, then
dy over dt over dx over dt?
mm-hmm. So dy over dt is equal to dy over dx times dx over dt, right? And remember, the easy way to remember this is because it's kind of like the dx's cancel, right? And you just get dy over dt. So that was one of the ways of writing the chain rule, if you remember from, way back when. Okay, now, but notice that dx over dt, what is that? Exactly, that's f prime of t, right? So this is dy over dx times dx over dt right here. This is f prime of t, right? And so, wait, are you guys okay? You can't see anything? Oh, is it because the screen is crappy? Yeah. I'm sorry. Couldn't get a better one. Okay, so so notice, let's combine these last two. This one and this one. So if I put those together, g prime of t is equal to dy over dx times f prime of t. So that means that dy over dx is equal to g prime of t over f prime of t, right? We just solved for it, right? And you can also write this as, it's probably easier to see it as g prime of t, that's dy over dt over dx over dt. So this is the slope of the tangent line. Okay, so let's do an example. Let's see. So let's see. Let's say for example you have, what did I write down? Okay. So I wrote down, I think, I have cosine of 2t and then sine of 3t. And then let's say we want to find all points where the tangent line is horizontal or vertical. Okay, so first off, what does it mean? How do you know that the tangent line is horizontal? So if dy over dx is equal to 0, how do you know if the tangent line is vertical? Yeah, if it's divided by, so if you find the derivative, if you find the places where the denominator is equal to 0, then that means that you have the slope of the tangent line is infinite, right? You guys remember that? Or, so either the denominator is equal to 0 or dx over dy is equal to 0. So one of the two. But since we're going to find the derivative, it's easier to just look at the denominator to find the vertical asymptote. Yes? Okay, so off we go. Derivative. So dy over dx is equal to dy over dt over dx over dt. So what is y in this case? Sine of 3t. Okay. So then that means that that dy over dt is equal to
3 times cosine of 3t.
3 cosine of 3t. Okay. And then dx over dt. So I know x is equal to cosine of 2t. Right? So dx over dt would be negative 2 sine of 2t. Okay, so all right, how about we do horizontal first? So we know that the tangent line is horizontal when the derivative is equal to 0, or in other words, whenever 3 cosine of 3t is equal to 0, right? And so where would that be?
Pi 2. Pi over 6.
Well, yeah, pi over 6, right? So it's because it's when 3t is pi over 2, right? So then that would be, so when 3t is equal to pi over 2, or 3 pi over 2, and so on and so forth, right? And then this is plus or minus, right? So that means that it's horizontal at t equals to pi over 6, pi over
3 pi over 2.
pi over 2, right? And so what would that look like? Do you guys remember how to write that from way back when?
There's a k in this.
K minus.
So this is, it's always good to review these things. So notice that you have a, whenever it's at pi over 2 plus or minus pi, right? So it's pi over 2 plus or minus k times pi, right? And then if you divide that by 3, right, because that's when 3t is equal to that. So that means that when t is pi over 6 plus or minus,
K pi over 3.
exactly, k pi over 3, right? Does that make sense?
Mm-hmm.
K equals 0, 1, 2. Okay. And then it's vertical when the denominator is equal to 0. So in this case, when negative 2 sine of 2t equals to 0, or in other words, just when sine of 2t is equal to 0. And that means that 2t has to equal to, what would that be?
0,
Multiples of pi, right?
Yeah, k pi.
So k pi, right? Plus or minus. So then that means that t is equal to plus or minus
K pi over 2.
k pi over 2, right? For k equals 0, 1, 2. Does that make sense? Thumbs up? Semi?
Why
Sort
is
of.
that only it's not 2 sine 2t for the vertical?
What seems like
Well, yeah, so all you want is the whole thing to equal to 0. So as long as sine of 2t equals to 0, because the negative 2 doesn't affect anything. So questions? So I know the screen is not very good there. Yeah.
What kind of application for these things are you going to use for?
All kinds. The thing is that there are a lot of situations where you need a parametric curve to describe some situation. Yeah, I mean, yeah, all kinds of stuff. because not everything is going to be something that you can write y in terms of x, or x in terms of y. So, just looking at the few pictures that we saw, you can see all the different possibilities that you can have and how much more free you are to produce all kinds of things. So I think we'll end there for the day. Early spring break for you.